Yes, if you're able to say both the classes summary, it will be very good, or at least you should be able to say. Yes, students, please, any one of you on your voluntary basis, you can just give me what I taught in the previous class. Yes, I'm asking you people only. Hello. Hope
Sir,
everyone is
time
there.
synchronization and frequency synchronization.
Very good, very good. Okay, I appreciate your support. Okay, so this is what required for teacher. At least if you are able to say title, then we think okay, something is there in their mind. Hmm? So even I'm finding others why they are not talking. I don't know. Okay. See here, why I go in one sequence is means if I want to teach the upcoming chapters, I will be talking or I will be using the terms what I am teaching now, right? It may seem sometimes okay, just for examination point of view, this is not required, this is required, and all. But for understanding, as far as you need to have some sequence, right? Some flow. So keeping that in mind, I covered complete module one without leaving any topic. In the module two, I think I will take one part, then I will take the flow to channels and other things. So I think with that you will be able to understand. Fine. Oh, fine. So just to say from my side, what I discussed yesterday. Again, I started with the cyclic prefix, right, in the OFDM. How does it helps to eliminate intersymbol interference within an OFDM symbol, right? And then I discussed about time and frequency synchronization. Before that, I discussed about the use of OFDM in LTE, right, and LTE parameters also. So this is what the block diagram of OFDM. Okay. Then how do we use that OFDM in LTE? I discussed this. Then these are some parameters with respect to a bandwidth of 10 megahertz, right? Uh, at least if you are able to grasp what is what, then in the upcoming discussions you will be able to understand, right? When I took the example, right, when L is equal to 128, what how many uh, cyclic prefix bits I use, and when L is equal to 2048, how many cyclic prefix bits I need to use, right? And with that, we came to know that what is the rate loss and at what percent it is, right? It is for both the cases, it is around 7%. So with respect to that, we say means how do we calculate that guard time, right? So which is equal to 144 into sample time. This is for normal cyclic prefix, and 160 into TS for extended cyclic prefix, right? So with this basic understanding, then I said about the timing and frequency synchronization is one of the most challenging problem in the OFDM implementation. Okay, so still people keep working on this to develop a better synchronization algorithm. Okay, so that it will use the is the task of our difficulties in OFDM. Fine. So first of all, we need to understand why do we need this timing and frequency synchronization. Is it possible to say any one of you why do we go for timing and frequency synchronization? Why it is required? Yes, I'm asking You people, is it possible to say why timing and frequency synchronization is required?
So possibly to avoid interference.
Yeah, that is one thing.
To demodulate the OFDM signals.
Yeah, yes, in order to demodulate an OFDM signal, so these are the two important tasks which need to be performed. One is timing synchronization, another one is frequency synchronization, as you said, and even one of your friend said for avoiding the interference. That is also correct, right? So here two things are there, right? I said one is the timing offset of the symbol and the optimal timing instance. So these two things need to be determined as far as timing synchronization is required. Okay, I repeat once again, the timing offset of the symbol. What is the timing offset of the symbol? Anybody is having any idea? See, we know what is the symbol time. In case of here LTE, the symbol time will be equal to 1 over 15 kilohertz. So, which is equal to how much you will get? Any one of you can say 1 over 15 kilohertz, because the subcarrier spacing is 15 kilohertz, we say. So, 1 by 15 kilohertz will give you the symbol time.
So 66 megahertz.
Symbol time, when I'm saying time, I think you should be able
Yeah,
to tell
sorry.
in terms
Yeah,
of
yeah. Yes, sir.
microseconds, right? So,
Yeah, yes.
66.67 microseconds. Am I correct?
Yes,
Yes,
sir.
sir.
Yeah. So because the subcarrier spacing is 15 kilohertz, so the symbol time will be 66.67 microseconds, right? So every symbol duration will be that much. In addition to that, there will be cyclic prefix duration also. Okay, that is of around 5 microseconds, we say. So by adding that 66 plus 5 microseconds, it will be around 71 microseconds we will get. So that will be total, we say, the symbol duration in OFDM. Okay. So as I said, since the channel is wireless, when it is when the transmitted signal reaching the receiver, it will be reaching through different paths, right? So there will be delay spread and other things. So at the receiver, there should not be any change in this symbol duration. Okay, there should not be any offset. That is what that timing offset of the symbol is. And optimal timing instant. Optimal timing instant means what? At what time we need to sample the signal, right, to decide about whether the received symbol is 0 or 1. So that is one. So that is the first task that we call it as a timing synchronization. Okay, hope I clear what is timing synchronization. The timing offset of the symbol and optimal timing instance are known as the timing synchronization. And second thing is, the receiver must align its carrier frequency as closely as possible with the transmitted carrier frequency. Okay, means whatever the carrier frequency I'm using at the receiver side, that carrier frequency should be aligned to the transmitted carrier frequency. Okay, so that we call it as a frequency synchronization. But in case of this timing synchronization, as I said, will not have much impact in case of OFDM because of the cyclic prefix and other things. But frequency synchronization is an very plays a significant and more stringent role here. Okay, if there is any shift in the frequency synchronization, it leads to inter-carrier interference. I hope we will be able to see those two waveforms here. So this is the time domain waveform of OFDM, what I have shown the first diagram, and second one is the frequency domain waveform of the OFDM. So you are able to understand. So what is perfect synchronization, which is sampled at exactly the peak of the signal. And when do we say it is imperfect synchronization? If there is a deviation from that peak value. then we say there is a imperfect synchronization of the carrier signal which is there at the receiver with respect to the transmitted carrier frequency. So that leads to inter-carrier interference. How do we minimize that? So that is the challenge. Okay, how do we minimize the inter-carrier interference if there is any shift in the frequency of the carrier signal which is at the receiver when it compared to the transmitted carrier frequency, right? So if it is a perfect synchronization, yes, ICI is 0, what I can say. Fine. Then I talked about this timing synchronization margin, right? So anyhow, we are keeping some amount of cyclic prefix, right, for avoiding ISI, inter-symbol interference. And in addition to that, even we take care of this timing synchronization margin also. So that value will be what we denote as tau. So that is the difference of this guard time minus the delay spread. If that value is less than this difference, then there will be no issue. Means it is perfect. If that is greater than this value, then it leads to problem, right? So because of this cyclic prefix, and usually the length of the cyclic prefix is much greater than the uh, time reference of this tau z minus tau m, so there will be a no issue. Okay. So just to give an idea, I told about the primary synchronization signal and secondary synchronization signal, right? And just I told these words. So we will discuss about this, what is the primary synchronization signal and secondary synchronization signal, how these two signals are important as far as this time and frequency synchronization is concerned. Okay, just to say, in case of this OFDM, there will be 31 tones, okay, on either side of the DC subcarrier will be used for this primary and secondary synchronization signals. So totally 32 tones, 31 on one side and another 31 on another side. So totally 62 tones will be used as synchronization signals. So each of what 15 kilohertz. So 62 into 15 kilohertz will get, I think, around 930 kilohertz. Okay, so 930 kilohertz is the bandwidth what we can say which is used for synchronization. Okay, so usually we can achieve the timing synchronization roughly around 0.1, means 1/10. Okay, 1/10 of the synchronization bandwidth. With that, since I said it is coming around 1 megahertz, so the value of that tau, whatever the timing synchronization margin I say now, so it will be of around 0.1 microseconds. So that 0.1 microsecond will be much smaller than the cyclic prefix duration. As I said, cyclic prefix duration will be of 5 microseconds. So in that way, we say the timing synchronization is not an issue in case of OFDM. Okay, so with this brief understanding about timing synchronization, and I will come back to frequency synchronization later on. Okay, so let me now take up the next topic, which is known as peak to average ratio. Okay, peak to average ratio. Yeah, I think I discussed about this in brief when I was talking in the earlier lectures. Is it possible to say, any one of you, what it is? PAR, peak to average ratio. In case of, you know what is the peak to average ratio for single carrier system? Or single carrier signals? See, peak to average ratio. So means it is a ratio of what? Peak power to the average power. Yes or no? In the name only it is there. Peak to average means we need to find out what is the peak power of that signal and what is the average power of that signal. You take the ratio of that. That is what the value of peak to average ratio. So is it possible to say what is the peak to average ratio for a single carrier signal, what I said? Then we'll discuss about the value for peak to average ratio for multi-carrier signal, that is for OFDM signal. Yes, quickly, any one of you, is it possible to say what is the peak to average ratio for a single carrier signal? Yes, my dear students, are you aware of that or not? Hello, I said what is peak to average ratio, right? It is a ratio of peak power of a signal to the average power of a signal. Let us consider the BPSK signal only. Is it possible to say what is the peak to average ratio of the BPSK signal? Yes. Yes, I'm asking you people only. If you are aware, you say yes. Something. If you're not aware, you can say you don't know. Even I defined what is that peak to average ratio. Fine. Let me. I think that is what. See, if with this basic knowledge, it's very difficult to make you understand as per the text. If I go, okay. So that is why I add here and there to make you understand from different sources, so you don't feel that it is not there as per video. Okay, don't think like that. Fine, let me just say what is the peak to average ratio for a single carrier signal. Okay, or a single signal, right? uh, yeah, is it visible what I am showing? Hello? Yes, I am asking, is it visible?
Yes.
Visible, huh?
Yes, sir.
Yes, sir.
Yeah, so I am talking about the non OFDM signal. Okay, so I'm considering a non OFDM, or we say it is a single carrier system, right? So I'm considering BPSK modulated symbols. So I write that BPSK modulated symbol as what? Hope you will be able to understand this small x of 0, x of 1, x of 2, and so on. This is right. So x of 0 may be plus a, and x of 1 may be minus a, and so on. Okay, because why I say it is plus a minus a, it may be 0 1 0 1. Okay, 0 I transmit with no phase, and 1 I transmit with 1 degree phase shift. With respect to that, I say here zeros and ones are occurring with equal probability. That is why I'm treating this as plus a and minus a, plus a minus a, and so on, right? So how do I find the power in each symbol? Power in each symbol will be equal to what I can say, it is a square. Okay, power. So that is what the peak power is. And how do I find the average power? That is the, because since it is all random variables, right? So since they are random variables, I need to take the expectation of this. So that is why it is written E of x of k, its magnitude square, right? So which is also equal to a square. Hope able to understand what I am saying. I took a non OFDM signal, which is what, the single carrier system. I have taken an example of BPSK signal, right? BPSK modulated signal. I just written these are the different symbols, x of 0, x of 1, x of 2, and so on. How do I represent x of 0? By plus a, x of 1 by minus a. I said what is this plus a and minus a? Right, in BPSK, we represent symbol 0 and 1 with this magnitude plus a and minus a. Plus a for maybe symbol 1 and minus a for symbol 0 and so on, right? So I said power in each symbol, which is equal to what I can say, it is a square. Okay, so that is what the peak power. And since these are all the random variables, means it occurs randomly, that is why to find the average power, I need to take the expectation of this random variable. So expectation of that is also a square. Then, so this is my peak power and this is the average power. So what I can say, the peak to average ratio for a single carrier system, which is equal to 1, I can say. right? So peak power is a square and average power is also a square. With that, uh, I can say the peak to average ratio is 1, which is nothing but 0 dB. In terms of dB, it will be 0 dB. Okay. Yes, is it clear what I said? So in the single carrier system, both peak and average power, which is equal to a square, that is why that peak to average ratio, that is peak power to average power, becomes 1, which is nothing but 0 dB, I say in terms of dBs. Hence, there is no significant deviation from the mean power level in case of single carrier system. Means there is, right, when the modulated signal is there, means there will be not much variation its mean value. Okay, it will be at the mean value. But let me consider the OFDM. Uh, yes, is it fine what I am saying? Hello.
Yes, sir.
Yeah, I will. Before I show this, I will just go and show you the. Uh, yeah, I think I will take up this slide. Hope this diagram is visible.
Yes, sir.
Yeah, just take time. Take 2 minutes time. Uh, means here. So these are all the different OFDM symbols, right? I said no, F naught is equal to 15 kilohertz and its duration will be of 66.67 microseconds. And see, we are using around 12 sub carriers, each of 15 kilohertz. First one is 15 kilohertz, next one is 30, next one is 45, like that. 45 plus 15 is 60 up to 180 kilohertz, right? So there will be 12 sub carriers we are using, and each sub carrier spacing is of how much? 15 kilohertz, and this is how the signal looks. Okay, H1 into X naught, then H2 into X2, like that, right? Able to understand this diagram? What is this one? This is the OFDM modulated signal. Okay, and together, if I write, so this is what it looks like. G of t means, see here, I am taking this as my reference, right? So there will be variations in the peak of the modulated signal, waveform signal. Okay, and if I take this is the average value, okay, from its average, you are able to see that the variations, how there is a fluctuations in the peak of the signal. Yes. So this is total OFDM modulated signal by considering all 12 subcarriers together. Here, in this example, shown only 3 carriers. Okay, this is a final 180 kilohertz. Okay, some 4 I have taken for understanding. So all together, when we mix up the final signal, which is looks like this. So there will be variation in the peak of this modulated signal. Yes, I'm asking, are you able to understand this point? Able to visualize why I am talking about peak to average ratio, to get that idea how the peak of the OFDM signal varies with respect to its average value. So here I have not written that average line, right? In the second diagram, it is shown that average value. Fine. So I have taken this as my average line. From that point, you just, if you understand how there is a variation in the peak of the OFDM symbol with respect to average, right? So we find the peak value is more, right? So it is not uniform. It is not uniform like this, right? So there is a variations in the peak of the OFDM signal with respect to its average value. So that leads to what? So many uh, difficulties. Okay, let me try to explain that. At least hope you could visualize this diagram. Yes, my dear students, please respond. I tried my level best to make you understand by giving the clarity in the picture. This is what the final OFDM signal. I'm talking about how there is an variations in the peak of this OFDM signal. Why there is a variations of so much in the peak of the OFDM signal? So that is also a question. I will come to that answer. Yes, no response. I don't know whether I should show this diagram or not. Hello?
Yes, sir.
Any questions with respect to this? This is what I said. The OFDM signal, OFDM modulated signal all together with 12 subcarriers. I said there is a lot of variations in the peak of this signal, right? Are you able to see that? Variations in the peak of the signal. It is not. So here I have taken that average value. From that average value, there is a lot of variations in the peak of the signal. So this is what is known as, that is why we call the OFDM signal is having high peak to average ratio. High peak to average ratio. I will say why it is having high peak to average ratio, because of what operation. Hope we are able to get this visualization. Hello?
Yes, sir.
Yes, sir.
Yeah, please respond. No, otherwise my effort will go waste, I feel. Without showing this diagram, just if I keep on talking about peak to average ratio, you may not. Okay. Fine. I think, okay. Yeah, I will come back to that. So now let me just say, yeah, I was with OFDM. No? I told why, how the peak to average ratio in single carrier system is 1 and it is 0 dB, right? Because peak power and as well as average power is equal to same. Means with respect to BPSK, it was just A square and A square. I said its ratio will be 1 and it is as good as 0 dB. Hence, there is no much impact of that on the modulated signal. So if I consider OFDM system, how do I find what is the peak to average power ratio in OFDM? So let me take these are the information symbols, x of 0, x of 1, x of 2. Hope so. This is the vector x. Just I used to say no vector x, capital X, right? So this is what that vector is. So these information symbols are loaded onto the subcarriers, right? That is what we do IFFT, right? So let me represent again. Take with BPSK modulation. This x of 0 may be plus a or minus a, right? Right, it may be plus a or minus a. Similarly, x of 1 also and x of 2 and so on, right? Means why I say it is plus or minus a, it may be 0 or 1, right? If it is 0, I can represent by plus a. If the symbol is 1, I can represent by minus a. So with that, yeah, I think you are aware of this. What we do that x vector will be passed through IFFT, right? So x of 0, x of 1 and up to x of n minus 1, these are the information symbols. We pass that through this IFFT. We get, when we pass it through an IFFT, we get the time domain signals, right? Which are denoted by small x, small vector x. So here I have written that x of 0, x of 1 and so on up to x of n minus 1. So these are the what? IFFT samples of the information symbols. Hence, what I can say, the transmitted samples are what? X of 0, x of 1 up to x of n minus 1, which are what? IFFT samples of the information symbols x of 0, x of 1 and so on up to x of n minus 1. Hope this is helping you people to understand. See, x of 0, x of 1 up to x of n minus 1. It's a x vector. So these are information symbols, right? I pass that through an IFFT. So you need to understand what IFFT block is having, right? So output of that will be what? Again, a vector which is denoted by small x. So here it is written x of 0, x of 1 out, x of n minus 1. So these are the IFFT samples of the information symbols, right? Okay. Yeah. So now to find out what is the peak power and what is the average power, right? And this is what we write, x of k is equal to that formula. So this is the IFFT formula, you know, right? 1 by n summation I equal to 0 to n minus 1 x of I e power j 2 pi ki by n, right? So this x of I, capital X of I, is my information symbol, right? And this x of k, small x of k, is my k IFFT sample, right? So the average power of this will be, again, since it is a random, right, random variable, I take the expectation value of that. So e of x of k mod square. So if I take the expectation of this, what I can get, 1 by n summation of that, and expectation of this. So expectation of this exponential power factor will be equal to 1, we say. The expectation of this exponential factor will be equal to 1. Then, so this is what the average power is. I will say with value, yes. Yeah. So the expectation, that is average value, right? Average power will be equal to what I say. This is what the expression. I think earlier, I think n square is this. Okay, 1 by n square into this, and this x of I will be what? A square, right? It may be plus a or minus a set. With respect to that, it is a square. So 1 by n square into summation I equal to 0 to n minus 1 a square. It is nothing but 1 by n square into a square n. So n, here n will over. So it will be what? A square by n is the average power of the transmitted signal. Okay. So average power of that one particular information symbol in case of OFDM will be equal to what? A square by n. So please try to understand this. So this is an important thing. So average power, what I said, it is a square by n. Similarly, the peak power. Okay, peak power. How do I calculate the peak power? This is what the peak power is. So peak power means by considering one particular symbol. Okay, when k equal to 0, I found here. When k equal to 0, so this is what the expression we can write. And I am thinking that is for x of 0, right? That is which varies from 0 to n minus 1. I can equate it to plus a. With that, if I substitute the value of x of 0 as a, so with respect to that, what I get, a is the this one, right? So the peak power will be equal to a square. Okay, the peak power will be equal to a square, and I found the average power will be a square by n. So if I take the average ratio, peak to average power ratio, it will be what? A square divided by a square by n, right? So a square divided by a square by n is the peak to average power ratio for that OFDM symbol. Means here a square will get cancelled. It will be equal to n. What is this n? Is the OF. So this is what the peak to average power ratio in case of OFDM system. And this n is the what number of subcarriers. Okay, so don't confuse with the notations. So far I used to say L is the number of subcarriers. So since I have taken it from different source, so they have used n as number of subcarriers. So please try to understand here, this capital N is nothing but the number of subcarriers. So the peak to average power ratio of OFDM system is equal to the number of subcarriers what we use. So now we understand, if we increase the number of subcarriers, the peak to average power ratio also increases, right? So it directly depends on the number of subcarriers what we use. So what is the problem in having high peak to average power ratio, right? So I will come to that now. Okay, as I said already, the peak to average power ratio increases with the number of subcarriers. Fine. So the high peak to average power ratio in an OFDM system, okay, essentially arises because of what? Why the peak to average power ratio in case of OFDM system is high? Because of this IF50 operation, what we do at the beginning. Okay. So when we do the IF50 operation, because of that, we get this high peak to average power ratio. Means the data symbols across the subcarriers, right, can add up to produce the high peak value signal. Because what we are going to do, we are going to divide the wideband signal into L subbands, right? So B by L will be the bandwidth. So we are going to create N subcarriers or L subcarriers, what we say. So with that, there will be, hope you are able to get my point. Because of this IF50 operation, okay, what we carry out in OFDM, that leads to high peak to average power ratio, right? So the data symbols across subcarriers can add up to produce a high peak value signal. So with that, okay, so here taken an example by taking an number of subcarriers which is equal to 512 and with BPSK modulation, okay, and it is found that the peak to average power ratio at the output will be as high as around 10 dB, okay, so which is more. uh, Fine. So the peak to average power ratio of an OFDM system, uh, okay, I think okay, how do we characterize this? So we do the characterization of this peak to average power ratio by using this complementary cumulative distribution function. Hope you are aware of this function, distribution function, complementary cumulative distribution function. At least you are aware of cumulative distribution function, na? CDF. Yes, are you aware of cumulative distribution function or not? Hello. Hello, my dear students. Are you aware of CDF? I'm asking. I don't know. You all may be feeling I am going somewhere else. Is it so? Do you all feel is it relevant or irrelevant? Hello. ಯಾರು ಮಾತಾಡೋದೇ ಇಲ್ವಲ್ರಿ? What I should understand, whether you are with me or not. Yes, my dear students, respond no. Hello. Hello illa bye. Yes. Is it possible to unmute and talk to me? What I am saying, is it fine?
Yes, sir.
See, this understanding without knowing how do we say all these things, you just go through the book, you will understand the difficulties. Huh? You people don't appreciate the effort of a teacher, don't communicate only. Thank you, Suhas Reddy. At least you are responding. Fine. As I said, we characterize the peak to average power ratio of the OFDM system by using complementary cumulative distribution function. So this complementary cumulative distribution function, when we use and all, you should know. Okay. With so many distribution functions, why do we select complementary cumulative distribution function? So this is how the complementary cumulative distribution function looks like. Okay. So x-axis will be the value of peak to average power ratio. And okay, so this is what the function what we write. So when do we use this complementary cumulative distribution function is when the probability of the random variable, okay, x is greater than its sample value. So this is what the PAPR is, and this is what the typical complementary cumulative distribution function curve is. Means as at 0 it should be 1, it should be maximum, okay, and as the value increases, this value also goes decreasing, okay. So for ideal PAPR characteristic, it should be at this point, means at 0 it should be 1 for ideal. So since it is non-ideal, so as the value of PAPR increases, its value keeps decreasing, okay. So this is what the curve of CCDF we say. So from this we will be able to say what is the value of PAPR. Okay, let me skip this. Yeah. Okay, so to understand what is the effect of this PAPR, okay, on the OFDM system, fine. Yes, able to see my slide, what I said? Yeah. So let me try to say what is the effect of this PAPR. Okay. So what is the effect of PAPR on the OFDM system? We all know what is the characteristics of the amplifier. Of course, many things are written here. So try to visualize first x-axis and y-axis. Let me write. So x-axis is the input voltage and y-axis is the output voltage, right? So how do I write the characteristics of the amplifier? Any one of you can say what is the ideal characteristics of the amplifier? Yes. Yes, I think for this I expect you to answer. Hello. Other people should respond. What is this?
Yes, sir.
Yeah, what is the characteristics of the amplifier? I said I have written many things in this. Please let me try to explain this, an important thing to understand. Yeah. Is it possible to say, Ritika? I said the x-axis is input voltage and y-axis is the output voltage. So usually we write the linear curve, right? Means as the input voltage increases, the output voltage also should increase. That is what we expect in the amplifier, right? Hope you are understanding what I am saying.
Yes, sir.
So it should be a linear curve. So that is what the ideal characteristics. But the practically after certain input voltage, it is getting saturated. So that is what this curve is shown. I am moving the cursor now. So this is what the characteristics of the practical amplifier. So it is after certain voltage, after certain input voltage, it is getting saturated. Okay, so output goes to non-linear region, what I can say. So this is what the ideal characteristics of an amplifier. So straight line it should be, right? And wherever till it is linear, no, that we call as a linear range or dynamic range. Okay, and this much we call as the non-linear or saturation region of the amplifier. So that you all know very well, right? So when it is getting saturated, means it becomes constant, right? Even if you increase the input voltage, there will be no change in the output voltage. That is why we said the saturation region. So output becomes non-linear. So we all know where do we select the operating point of an amplifier, right? If at all we want to amplify the signal faithfully without any distortion, it has to be at the center of the load line, what we talk, right? If it is at the center of the load line, then it is possible to amplify the signal without any distortions, right? Means without any clipping of the signal, either positive peak or negative peak. But what happens in case of OFDM, because of this high peak to average power ratio, no? So what happens? It goes to non-linear region. Okay. The yes, if its average value is within this linear region, then there will be no issue. But in case of OFDM, what happens? It will be extending to non-linear region because from its average value, because of the high peak high peak to average power ratio region. So that leads to the demand for uh, power amplifiers. Okay, we all know the high power amplifier extending its linear region, because power amplifier is one of the main component in the uh, transmitter part, right? So, and basically it is a non-linear device, right? So to extend the linearity of the amplifier, or even uh, uh, means when I pass this high peak signal, no, I said the non-linear device, which is known as a high power amplifier, or even the digital to analog converter. So what happens here, when it is going to the non-linear region, it will be creating the intercarrier interference. Okay, so this high peak to average power ratio leads to many problems, I used to say, right? So it will be generating out of band energy, that we call it as spectral regrowth, and as well as the in band distortion. So in band distortion is known as means there will be tilt in the constellation, and as well as scattering of the constellation. So to overcome those problems, we need to means when the constellation size is tilting, and what I said, no, it will be generating out of band energy, right? All these things will be leading to degrade the performance of the system. Okay, so means the high power amplifier extending the linear region is a big challenge. Okay, means we need to spend means to increase the resolution of a DAC is also a challenge, right? So these are all the difficulties which we face if the value of peak to average power ratio is high. That is what I wanted to convey. Okay, so in OFDM, when the peak deviation about the average is significantly high, I said the signal level moves outside the dynamic linear range. So this high peak to average power ratio in OFDM results in what I said, amplifier saturation, that leads to intercarrier interference. Okay, I think with this I will, yeah, I will not say this as of now. Fine. Uh, Hope I conveyed what is the effect of peak to average power ratio in OFDM system. With respect to this characteristics of the amplifier is concerned, what I said. Yes, any one of you can say what I said. Because of high peak to average power ratio in OFDM, it will drive the high power amplifier, what we use in transmitter, into the saturation mode. That leads to what? Intercarrier interference. So that one only I told in a different language. That is, I said it creates or generates out of band energy. So that is known as the spectral regrowth, and as well as it creates in-band distortion. So that in-band distortion is known as constellation tilting and as well as scattering. Okay, then how do we overcome this problem? For that there is a solution. Okay, it is acceptable for downlink transmission. That is why OFDMA has been used for downlink transmission, but not for uplink. Because why they still use this OFDMA for downlink is because uh, downlink is what? Any one of you can say? Downlink transmission means what you understand? Is it from user equipment to the base station? What I mean to say, mobile to base station, or from base station to mobile? The
BTS to
signal
mobile.
transmission. Yes.
BTS to mobile, sir.
Yeah, BTS to mobile, right? So downlink transmission is what one of your friends said. It is the signal transmission from BTS to mobile station. So the number of base stations will be less when compared to the number of mobiles, and it is possible to use costly uh, high power amplifier in case of base stations, because it can uh, serve many users, right? But it means the cost can be spared there, but not in the mobile device. because we know how much it factors, means it costs, right? We cannot think of using high cost power amplifier in the mobile device. So that is why for uplink, so different multiple access technique has been implemented, that is known as SC-FDMA, that is single carrier frequency division multiple access. So before that, what we say, it is a single carrier frequency domain equalization. Okay, that is with respect to single carrier, what I say. So I will take up that one next. So hope I could convince what is PAPR. If you have understood this, is fine. It is very important also. Just I would like to throw some light on this OFDM, okay? Because I feel like explaining this, try to understand. Yeah, able to see my slide? Yes.
Yes, sir.
Yeah. So I think some 2-3 slides are there. I hope that will make you get clarity about what OFDM is. So there's a time axis and frequency is there, right? Y axis is the frequency. I said no. The subcarrier spacing is 15 kilohertz, right? So first one is 15 kilohertz, next is 30, then 45, 60, and so on up to 180 kilohertz. So there are 12 subcarriers. Okay, so 12 subcarriers, and so this is what one OFDM symbol is. So 0 to T is written. That is one OFDM symbol. So which is equal to what I said, 1 by 15 kilohertz, which will give you 66.67 microseconds in terms of time. So this is without cyclic prefix duration. Okay, if I add a cyclic prefix duration, it becomes 71 microseconds in reality. So these are all, means if I see here, it is shown with how many, 1, 2, 3, 4 subcarriers values. Okay, one is 15, okay, another is 30, then 45, then 180 kilohertz. So together, by adding, this is what the OFDM signal will look like. So like that, we can think of all 12 subcarriers, right, with different, means you able to understand this. This is at 15 kilohertz with a magnitude of 1.4 volts amplitude, right? This is at 30 kilohertz. That is why the number of cycles is doubled. Okay, then this one is at 45. When compared to first one, it will be 3 times of that. So similarly, it is 180. So just think how many cycles will be there with respect to that, with respect to the first one. Okay, so that is the last one is the sum of all these signals. That is what OFDM signal will look like. So this is how we divide. I will take up the next slide. I think able to get an idea, clarity. Yeah. So okay, this, whatever I've shown, this is in time domain. Okay, this is a time domain signal, and here what I've shown is in the frequency domain. So this is one window, right? What I was telling yesterday also during time synchronization, time domain waveforms I have shown. I think this with respect to some change in shift in frequency, right? So this is the time domain waveform, and so it exists from 0 to this much. So it is a rectangular pulse, what I can say. The Fourier transform of that will be a sinc function. So this is for first one. Okay, so I get peak value at 15 kilohertz. Hope you able to understand this. 15 kilohertz, I get a peak value. Then I will be getting the zero crossings, which exists for this time. So second one is at 30 kilohertz. So this is the time domain signal, and this is the frequency domain, right? So this is sinc function. So peak value will be at 30 kilohertz. Okay, this is the second one. Then third one is at 45 kilohertz, right? So at 45 kilohertz, I get a peak signal. Hope is it clear? And this is the what the third one. What I have shown is addition of these three. Okay, so this is how the OFDM signal will look like. Yes, my dear students, are you able to get this visualization with respect to each signal symbol in time domain? How does it looks, and in frequency domain, how does it looks? I have shown here by taking 3 symbols with together as one OFDM symbol with the 3 bits. Is this fine to understand to certain extent? able to visualize this? Hello? Again, no response. Hello?
Yes, sir.
Yeah, please try to understand. Okay. So, yeah. I think I will come back to this slide, I think, later on. Okay. How this about subframe, in one subframe, how many symbols will be there and all, I will take up next when I was discussing about frame structure and all. Okay, at least just you should be able to visualize this diagram. Fine, I think with this, let me stop for today's